Hello there, welcome to our first video on the Cretaceous mass extinction. So we'll start out by considering in this video the causes of this extinction, which incidentally have really nothing to do with getting trapped in holes in the ground. And in future videos you'll learn about the sort of the effects and what this extinction did to life at the time. So you've heard about mass extinctions before when we talked about the end-Permian mass extinction. So the end-Cretaceous one has been the most recent of the 5 large extinction events, and it's perhaps the most famous one, especially famous as the extinction that killed the dinosaurs. Although, as you now know, it didn't kill all the dinosaurs because birds are actually a group of dinosaurs, and they survived the extinction. So there were 2 major hypotheses for what caused the extinction. One is volcanic-driven climate change, which is similar to what you learned about the Permian extinction. And the other is that there was an asteroid impact. And so like some of the previous debates that you've heard about in this class, the vast majority of the scientific community supports one of these hypotheses, and a small group argues for the other. So let's look at the evidence for these. But first, a little detour to talk about how scientists determine the age of events in Earth's past, because we'll be looking at this for the Cretaceous extinction very shortly. So as I mentioned very briefly before, these ages are determined from the decay of radioactive elements. And so because of physics, radioactive elements decay at a steady and a known rate until they ultimately turn into a stable element. And so this rate can be described by something called a half-life. For example, if we start with, say, a million atoms of some radioactive element, after a time interval equal to 1 of these half-lives, there will only be half of the atoms left, and the other half would have decayed or changed into the stable element. And so after that, now we're down to half of our original amount, and so after another half-life interval has passed, a further half of the remaining atoms will have decayed, so we're down to a quarter, and then after another half-life, another half of the remaining ones have decayed, and so forth. So the 2 radioactive elements that are used for dating of geological events primarily are potassium-40, which partly decays to argon-40, and this is used in a method called argon-argon dating. And uranium is an important one. So there's 2 different types of radioactive uranium. They both decay to lead, and these are used in a method called uranium-lead dating. So looking at the Cretaceous extinction, there is a site in eastern Montana which has a little layer of volcanic ash that was deposited or that erupted at basically the same time as the extinction. So, this isn't many places, but at one place you can find a little volcanic ash layer there. So using the argon-argon dating method, on the crystals from that volcanic deposit, the researchers were able to determine that the extinction happened about 66.043 million years ago, plus or minus 40,000 years or so. So regular volcanoes don't cause extinctions. It takes something really exceptional, and that's in the form of these eruptions called flood basalts. And you've heard about these from the Permian extinction, but this is where you get huge amounts of lava that are erupted over geologically quite short time periods. The flood basalt that's associated with the end-Cretaceous extinction is one called the Deccan Traps, which covered a large area of western India with lava that ended up being about 2 miles thick. So it ends up being difficult to use radioactive dating on these kinds of lavas, but from what people have been able to figure out, the oldest lavas erupted about 66.288 million years ago, and eruptions continued until about 65.535 million years ago. So that time range does mean that it includes the extinction event at 66.043. There is still debate about when most of the lavas erupted. Did they mostly erupt before or after, or did they mostly erupt during the extinction itself? That's still a little bit uncertain. So there was an asteroid impact around this time. That's where this hypothesis comes from. And when it hit, it threw up lots of tiny bits of melted rock that cooled into these glassy things called tektites. And a glass just means it doesn't have a regular structure because it cooled very quickly. So dating of the tektites with the argon-argon method here showed that the impact occurred 66.039 million years ago, plus or minus about 50,000 years. So if we look at the timing of all of these things, can we tell which one was most likely the cause? Well, no, not exactly. Yeah, I mean, it does look like the impact and the extinction most likely happened at the same time based on their ages. They're not exactly the same, but with the error bars, it seems like they're pretty much the same. But maybe the Deccan traps also occurred then. I mean, they definitely were occurring during this interval. Maybe there were also a lot of eruptions right around this time. So we can't tell which was the most important cause just from this. Maybe it was actually kind of the combination of both of them. So I won't talk a huge amount about the asteroid impact because there's tons of evidence that it contributed to the extinction from sites all around the world, including many sites where scientists have drilled deep into the ocean floor to get deep sea sediment layers from the Cretaceous extinction. So at all these sites, the extinction happened at the same time as a layer containing a huge increase in the element iridium, and this element is common in asteroids but rare on Earth, as well as you can find in these layers bits of melted rock, these spherules and tektites, and also mineral crystals that show evidence of high-pressure shock waves that sort of broke them up and created all these little fractures in them. So the asteroid hit what is now the Yucatan Peninsula in Mexico, although the crater is now buried under lots of sediment that accumulated since the impact 66 million years ago. So in and near the impact crater, there's evidence for layers of melted and broken up rock called melt breccia. And throughout the Caribbean region, the impact caused huge tsunami waves and threw melted rock bits and chunks of rock thousands of miles away from the crater. So it's pretty clear that the impact was closely associated with the extinction. From all the evidence suggests that there was an impact at the same time. But what about the Deccan traps? Did it also contribute to this? Well, if you remember from the Permian extinction videos, volcanic-driven extinctions had this sort of consistent pattern of environmental change. And I'll focus on a few things for the Cretaceous. That would be carbon dioxide release, temperature increases, and ocean acidification. And there are other things, but we'll look at these three. So is there evidence for any of these factors during the Cretaceous extinction? So this figure compiles a whole bunch of different estimates of past temperatures from land, from the ocean, to try and look at temperature changes in the 1.5 million years or so around the extinction. Because these measurements all come from different places, they're all shown as what instead of like the actual numbers as a relative change. So this delta temperature is the change in temperature in that individual record. And so positive numbers mean it gets warmer, negative numbers means it gets colder. And so the records show that the temperatures did warm up by about 2 degrees, but that was before the extinction, from about 300,000 years before, or 0.3 million years, to about 200,000 years before the extinction. But then they kind of returned to the previous levels and didn't really actually change at the extinction itself, perhaps. Perhaps it was even a tiny bit of cooling at the extinction, but it's really, really tiny. So this isn't consistent with what we'd expect from volcanic-driven climate change. There's no large temperature increase at the time of the extinction. But kind of puzzlingly, there was a pH decrease of about 0.25 units that occurred very quickly at the same time as the extinction. It's hard to know exactly how quick, perhaps within 1,000 years, and then it recovered sort of back to normal within 10 or 20,000 years maybe. So this is interesting. This rapid ocean acidification, could this be consistent with carbon dioxide release from flood basalt volcanism? Yeah, I mean, it could. This is what we'd expect to see. This is what we see at the Permian extinction and other events of volcanic climate change. But is it the only explanation? So the asteroid did hit an area with lots of carbon rocks, carbonate rocks, and then also lots of sulfur-rich rocks. So perhaps this acidification is actually from sort of acid rain from the impact, from the sulfur, and also the carbon that could sort of go into the atmosphere and cause acidification over a slightly longer time scale. So this might be from the impact, and especially because we don't see any temperature change here. It's hard to know about this. Right, so the ocean acidification could be consistent with a volcanic climate change event, but there isn't a temperature increase, which is odd. So how about the carbon isotopes? Do they provide evidence for addition of carbon dioxide from volcanoes into the atmosphere? Well, so there is a negative shift in carbon isotopes, like we saw at the Permian extinction. However, this negative shift was very abrupt, so that's helpful, but it was only in shells from shallow water, which is sort of surprising. Actually, shells from deep water animals or deep water organisms actually instead had a small positive shift in the isotopes that they measured. So this is sort of a different sort of signal. And if you look at the period before the extinction, sort of in the latest part of the Cretaceous period, there's actually a clear difference in isotopes between shallow and deep water, but that difference goes away right after the extinction. So before the extinction, you can see the shallow and the deep are about 2 units different. Then they're the same after the extinction, and then after some time, after 500,000 years or a million years, they sort of recover that difference. So this actually suggests, and I'll explain why in a second, that the isotope changes were actually a result of the extinction itself, and that they don't indicate, rapid volcanic carbon dioxide release. So why do they indicate why are they caused by the extinction? How does this work? So first we have to understand why there was that difference in isotopes between surface water and deep water before the extinction. So remember that carbon comes in 2 different stable isotopes, the common carbon-12 and the rare carbon-13. So we'll start as a sort of a simple model where we have 2 boxes. We have a surface ocean and a deep ocean, and they'll both contain sort of what we would expect, this expected value of carbon-12 and carbon-13. And that's this value, this measure of delta 13C measures the relative amount of the 2 isotopes, of the 12 and the 13. And a value of 0 indicates that there's the expected amount sort of relative to a standard material that we're looking at. Positive values indicate that there's more carbon-13 than our expected amount, and negative values indicate that there's more carbon-12 than our expected amount. Okay, so plankton are taking carbon from the seawater and using it to make organic matter. And when they do that, they tend to take a bit more of the carbon-12 than you would expect them to do. So as a result, the carbon that's left over in the seawater has less of that carbon-12 and more carbon-13 than expected. So what does that do to the delta 13C value? Well, it will shift to more positive values because there's now more carbon-13 in a relative sense than we would expect because some of the carbon-12 has been taken away into the plankton. So some of this organic matter sinks after the plankton dies, and in a process that's called the biological pump. And then this organic matter, the part of it that sinks, will decay and be broken down in deep water, and that will release this carbon back into deep water now. So what will that do to the delta 13C value of our deep water box now? Well, it will shift it to slightly more negative values because the addition of this new carbon, which has slightly more carbon-12 than we started with, will mean that there's now more carbon-12 in our deep water box than we would expect there to be. And so finally, how can we tell what the ocean was like? Well, the shells of organisms record the isotope value of the seawater, of the carbon in the seawater. So scientists can look at organisms that float up at the surface of the ocean, as well as those that live on the seafloor in the deeper parts. Okay, so what happens if this biological pump is weaker after an extinction because so many things have been killed off? Well, that means that there's less organic carbon that's sinking, and now less of it is being removed from that surface ocean box, and less is being added to the deep ocean box. So what does this do? Well, as a result, this means that both the surface and the deep ocean will tend to return back towards the expected values, right? So instead of having these sort of offset values because carbon is being removed from the surface and added to the deep, that's happening less, And so they kind of go back to what we'd expect them to be, or sort of back from the circles, moving back towards the squares. And so that reversal will make the surface ocean shift from its slightly more positive value back in a negative direction towards the square. And the deep ocean will shift the other way. It'll shift from its slightly more negative value back up more positively towards the circle. Right, so if you remember, a couple slides back, that's exactly what we see after the extinction. The surface ocean has this negative shift, but the deep ocean has this sort of positive shift, and they both become more similar to each other as they both become kind of back to what you'd expect if you didn't have this biological pump going on. So this has been called the Strangelove Ocean, after the nuclear movie Dr. Strangelove. So what this tells us is that these carbon isotope changes don't demonstrate volcanic carbon dioxide addition, but were actually caused by the extinction itself. So there really isn't good evidence for volcanic climate change during the extinction. Instead, there seems to have been volcanic and environmental change perhaps before the extinction, but not really doing much, and it was the asteroid impact that was the trigger, the culprit that killed off all of our favorite dinosaurs and everyone. So that's what we'll learn about in the next videos. You'll learn about what the extinction did. So that's all for now, and thanks for listening.